Hello everyone, welcome to our last unit of AP Physics C, Electricity and Magnetism, and of AP Physics C as a whole, since we are already done with mechanics. This unit is on electromagnetism, basically taking what we learned in electricity and magnetism and combining them together. So it's one of my favorite units of E&M. This is going to be a pretty long video, even though this unit seems pretty short. There's just a lot to cover and a lot of complicated topics. After the content review, we're going to have 7 practice problems. So let's get started. The main thing that you should learn in E&M is what we're going to start with, which is Faraday's law and Lenz's law. Before we get into those specific laws, though, we need to talk about magnetic flux. We already know what electric flux is, so this is going to be similar. Magnetic flux is just the amount of magnetic field that goes through a certain area. And so the formula for this is just B times A, with a little caveat next to it. I'll get to it in a second. So this is given by phi of B. So this is the symbol for the magnetic flux. And that's equal to BA. Now, when you have angle, so let's say you're having your magnetic field and it's at an angle, theta, it's going to be times cosine theta, because this is kind of like a dot product, basically. Now, this is if magnetic field is constant. If magnetic field is time dependent, then your formula would look a bit different. It's going to be equal to the integral of B dot dA, like I said, dot product. And this encompasses the cosine theta because it's a dot product of two vectors. dA, as you probably know by now, is the area vector, which has a length that is equal to the area, and its direction is directly perpendicular to the surface. So yeah, this only works if it's time dependent. If it's a position dependent magnetic field, then you can't use this formula because that gets way too complex. For example, let's say this is your loop. If magnetic field changes over time, and yes, we are back to the x's. I'm probably going to draw way more x's than any other magnetic field symbol in this unit. It's just my favorite one of them, so we'll just stick with that. Yeah, so if you have this magnetic field is decreasing over time, then that's perfectly valid to calculate the magnetic flux. You're going to get a function of magnetic flux over time. But if instead it looks something like this, where the magnetic flux doesn't look evenly distributed. It's more concentrated here and less so here. So it's like, it depends on the position. Then you're going to have to use way more complicated calculus, not even in the scope of this class. So yeah, just brief interlude there. You're never going to come across a position-dependent magnetic field, but just in case. So what does magnetic flux have to do with anything? Especially what does it have to do with electricity? Well, that's where we get Faraday's law. Faraday's law basically says that if you have a magnetic flux, so if you have a change in the magnetic flux, which is a change in the amount of magnetic field that passes through a certain loop, then that's going to cause or induce an EMF in a nearby loop. So the most common diagram is this. You got this circuit that looks something like that, and let's say there's a battery there. That's a loop. You have a nearby loop that is connected to a potentiometer, which is just a device that measures small changes in current. You should have used them in class, but if you didn't, that's what it is. Now, if you change the magnetic flux, so I'm not going to get into the detail on how you do that, but let's say the amount of magnetic field that passes through this loop changes, then there's going to be a current or an EMF that is induced within this loop, and so there will also be a current if there's resistance in the loop, and in most cases this is going to be resistance because wires have resistance by themselves. So how can you change the magnetic flux? You can increase or decrease the magnetic field. You can increase or decrease the area of the loop. So if you make the loop bigger, then you're going to also change the magnetic flux. You can also change the orientation of loop. If you, for example, it starts off flat and then you change it to have an angle, that would change the cosine theta part of the formula. So You can change any of these three things, basically. A few key things to note. Let's say you, instead of this mechanism, you have just a bar magnet, north-south pole. Just putting a bar magnet next to a loop isn't enough, because that doesn't change the magnetic flux. That has a constant magnetic field that goes through the loop. It doesn't change, therefore there is no induced EMF. But if you move the bar magnet into the loop, or through the loop, closer to the loop, whatever, if there's a relative motion between the loop and the magnet, then induced EMF appears, because the magnetic field of a bar magnet looks something like this. So the magnetic field at this point is different than at this point. And so when you change the position of the loop with respect to the magnet, it's going to experience a different magnetic field. And so since the magnetic field changes, the magnetic flux changes, and so there would be an induced EMF. But once you stop the relative motion between them, the current disappears. It's not a sustained current, it's an induced, just for an instant current. When you move it faster, you're going to get a greater current, and we'll actually go into a similar example later on in the content review. And changing the direction of motion would change the direction of the current. If moving towards it causes a clockwise current, moving away would cause a counterclockwise current, and vice versa. Okay, let's get the bar magnet out of the way, and just consider these two loops that are next to each other. What is going to happen if we flip the switch? Currently the switch is open, meaning there is no current through here. If we flip the switch, what's going to happen? If you're struggling with this unit, you might want to pause, think about what you know about this unit already, unless you're watching this for the first time and learning these concepts for the first time, in which case I'll explain it to you in a second. But I would suggest you to pause and try to reason out yourself, because a lot of the AP exam questions are going to be like this, and the AP exam is coming pretty soon if you're watching it now. So yeah, try to reason through it. If it's like an FRQ, it might ask you, why is it going to be in this direction? And you're going to have to explain. You're going to have to reason through it. If it's an MCQ, just reasoning through it will help you with the MCQ. You might get it wrong if you have the wrong reasoning. So just take this time to practice. With that being said, I'm going to give you a second to pause. Okay. So what happens if you close the switch? You make it a whole circuit. Well, let's look at what the current in this is doing. Let's ignore the second loop for a second. The conventional current is going from the positive end of the battery, so it goes this way. It goes up, it goes clockwise in the loop, then it goes back down, and then that way. So current is going clockwise in this loop. That is the instant that it turns on. So before, there was no current, now there's a clockwise current, just in 1 second, right? Now, what does that have to do with the magnetic field and the magnetic flux that this loop experiences? So the magnetic field, we know from last unit that a current causes a magnetic field. And a clockwise current, you can use your right hand rule. You curl your fingers clockwise, your thumb points inwards. So the magnetic field would be inwards. It starts off at 0, then it becomes inwards, which means that is going to be the magnetic field that causes an induced EMF. Now, what direction is going to be the induced EMF or induced current in this other loop? We actually haven't learned that yet. There is a formula for this, or like a step-by-step process to determine the direction, and also a formula to get the magnitude, which I'm going to cover in a second. If you already know, try to figure it out. If not, I'm going to go over the equation and law in a second. So all we know for now is that the magnetic field points inward. It wasn't pointing inward before. It was 0 before, and then it starts to point inward. So there is a change in magnetic flux. The magnetic flux was 0, then it becomes then the magnetic field points inwards, which causes a magnetic flux change in the inward direction. So just keep that in mind for now. All right. So what is this Faraday's law? Faraday's law basically says that the EMF induced is equal to the negative derivative of the magnetic flux with respect to time. That's pretty much what we expected, because when we said there's a change in magnetic flux causes an induced EMF, well, a change in something with respect to time is basically just the derivative. And so the one weird thing is this negative sign. Why is there a negative sign there? And that is Lenz's law. So this equation technically without the negative sign, is Faraday's law. That's a more quantitative law that describes the magnitude of the induced EMF, which we don't need now because we don't know any values in this example right here. What we do need is Lenz's law, and that's this negative sign. It looks very innocent, very small. It's just a negative sign. But there's this whole set of rules you have to follow if you want to calculate the direction of the induced EMF. Just going it over one more time. Faraday's law finds the magnitude of the induced EMF. Lenz's law finds the direction of the induced EMF. So what exactly is Lenz's law and how would you use it? It's not just a simple negative sign. That only works if you actually have the values. Because what does the negative mean? It just, we just don't know yet. So Lenz's law basically says that the induced EMF or induced current has a direction such that the induced magnetic field opposes the change in magnetic flux. That was a mouthful. Let's get into that. Induced EMF and induced current are used interchangeably here because they both have the same direction. So let's just talk about current for a second. When you have an induced current, that's still a current, and we know from last unit that any current causes a magnetic field. And so this induced current will cause a magnetic field that is from this induced loop. From this loop, not this loop. This loop also has a magnetic field. This one's going to be the induced magnetic field. So that's also just going to be there for a second. Now, what Lenz's law says is that this induced magnetic field, the direction of that is going to be opposite the change in magnetic flux. So earlier I was saying the change in magnetic flux is inward. So our induced magnetic field should be outward. That's what Lenz's law says. It basically opposes the direction of the change in magnetic flux. That's going to be your change in magnetic field. Then you just use the right hand rule we learned from last unit to find the direction of the current. Your thumb points outward, so what way do your fingers crawl? It's going to be counterclockwise. And so that means the current is going to be moving in this direction, which is pretty cool. Lenz's law tells us all of that. Yeah, so it's basically opposing the change in magnetic flux. One little side note there, it's a very small thing. It's opposing the change in magnetic flux, not the change in magnetic field. Why is that? Why does that matter? I'll give you an example. First of all, the magnetic field might not even change. Let's say you have these, let's say we don't have two loops, just a magnetic field, and it's going to be axis. Right. We have a magnetic field going inwards, and the magnetic field doesn't change, but you just change the size of this. Might actually be helpful if I use a different color to show you differences in this unit. You just change the size of this. That's going to be changing magnetic flux because area is one of the things you can change, but it's not going to change the magnetic field. So if you were to use the changed magnetic field, there was no change. You might assume there's no induced EMF, but Lenz's law specifically says the change in magnetic flux. And since it started off inwards because the technically magnetic flux doesn't have a direction because it's a dot product, but if it did, it would have the direction of the change in magnetic field, if that makes sense. It's just going to be greater. It's going to have the direction of the magnetic field, and that can change depending also on the area. So in this case, I'm going to put this in heavy quotes because, again, it doesn't have a direction, but magnetic flux is going inwards. Again, it's not actually, but just for the sake of conceptually understanding what the change in magnetic flux means or the direction of that change, magnetic flux is going inwards, and since you increase the area, it's going inwards even more. It's increasing in that direction. And so the opposing of that change would mean a magnetic field, an induced magnetic field going outwards. If you were to decrease the area of this loop, then this is where it gets a bit tricky because magnetic field is going outwards or inwards and you're decreasing it. Magnetic flux, again, air quotes, would still be pointing inwards because that's still the direction the magnetic field is pointing in, but it's going to be smaller. The magnetic flux decreases, and so it would be pointing less inwards. And so the change would actually be outwards. The change in magnetic flux would be outwards. See, that's the key point. Even though the magnetic field is pointing inwards and the magnetic flux is, air quotes, pointing inwards, the change in magnetic flux is pointing outwards. So that's kind of what I was trying to get at here, where you don't worry about the direction that the magnetic field or flux is in. You care about the change of those. So the change in magnetic flux is pointing outwards, and so your induced magnetic field should be pointing inwards. Even though your original magnetic field is pointing inwards and still is pointing inwards, your induced would still be pointing inwards because the change is outwards. I just want to emphasize that a lot because that is one of the biggest problems with students learning Lenz's law. That's probably the most common mistake because everything else is just right hand rule and common sense of opposing direction. The only thing is what direction should it oppose? That's the change in magnetic flux. Change in. So yeah. Okay, let's talk about induction. Induction is a pretty big part of this unit. Again, happens when there's a change in magnetic flux. Specifically, we're going to be talking about moving loops. So that's going to be what's known as emotional EMF, which I think we named. But if we didn't name it, yeah, it's called emotional EMF because it's an EMF caused by motion of the loop. Pretty self-explanatory. So usually it's going to be something like this, where there's a magnetic field. It's usually one of two scenarios, actually. There's a magnetic field, and you have a loop. Part of it is outside the magnetic field, or sometimes it starts off completely in the magnetic field, and someone moves it. Either pushes it out, pushes it in. That's going to change, even though the area of the loop doesn't change, the area of the magnetic field going through the loop changes. Because currently, it's only this part of the magnetic loop, part of the loop that gets a magnetic field. If you bring it out a little bit more, then it's a smaller part. So the area of the loop doesn't change, but the area that the magnetic field goes through changes. So that keeping the same loop, same magnetic field can still change the magnetic flux. Obviously, orientation changes it, but even moving it beyond the magnetic field also changes. So what is the other type of problem? I mentioned that there were two types of problems you could get. One is this. The other one is everything's in the magnetic loop, but magnetic field, but instead of a loop, it's like 3/4 of a loop, and then a movable like segment that is like electrically connected, or not electrically connected. It's it touches the 3/4 loop so that a current can go through it completely because it's conductive. And you just change the position of this little rod. So that changes the area of the loop. So unlike this, which doesn't change the area of the loop, just the amount of the percent of the loop that a magnetic field goes through, this actually changes the area of the loop because you're moving it back and forth. So it's going to be one of those two. We are going to be looking at one of these in the practice problems. So because of that, let's look at this first example as an example problem in this content review. A lot of this content review is going to be examples, by the way, because I feel like the best way to learn this unit is through examples. Okay, so you are pulling this loop that way. A few constants you're going to want to know. You're pulling with so that the velocity or the speed of the loop is v, and the length of the loop is L. Length as in the upwards direction, because this changes. The amount, the width of the loop that is that undergoes a magnetic field changes because you're pulling it away. Let's just call that x for now, and x is x changes as a function of time, because you're pulling with constant velocity v. Obviously this is b. That's pretty much it. So you are pulling on it. That changes the magnetic flux. Let's see how it changes the magnetic flux. Magnetic field points inwards. You're decreasing the area of the loop that experiences a magnetic field. If you're decreasing the area, that means that's decreasing the magnetic flux. It doesn't point as inward as it used to, which means the change in magnetic flux would be outwards, not in just like this example we were doing before. Pay attention to that. The change in magnetic flux is outwards, and so the induced magnetic field would be inwards. The induced magnetic field due to that the induced EMF causes is going to be inwards. With that in mind, induced magnetic field is inwards. Let's use right hand rule. Thumb points inwards. Which way do your other fingers point? If I can draw that. They go clockwise, which means that the current is going to go this way, clockwise. The reason why I split into different segments, I'll get to in a second, because there's more we're going to do than just which way does the current point. There's actually a lot more we're going to do. So, direction of the induced EMF, aka current, is going to be clockwise. What else happens here, though? You got a current that is in a magnetic field. Not this induced magnetic field, but it's in a magnetic field. And what did we learn last unit? Well, currents can experience magnetic fields and experience magnetic forces. So let's look at each of these, except this one, because it's not in the magnetic field. That's pretty important. If on an FRQ you got a question like this, you would not calculate the force on this segment because it is not experiencing the magnetic field. That is the entire point of this question. If it was, then there wouldn't be an induced current because everything's in the magnetic field already. You're not changing the area that the magnetic field is going through. The entire point is that this part of the loop is not in the magnetic field. So we do not calculate the force on that. There is actually no force on that side of the loop, just the other sides. So let's start with this portion going upwards. Current goes upwards, so we put our fingers pointing upwards, and the thumb, it curls inwards because the magnetic field is inwards. So these just look like long fingernails, but you know what I mean. It curls inwards, and so that means our thumb has to be pointing to the left. That means that the magnetic force on that side of the loop is going to be, sorry for that bright green. Okay, is going to be pointing to the left. Let's do these other sides as well. So it's the top side is pointing to the right. Curl inwards, that means thumb is pointing up. That's the direction of the magnetic force. For the bottom side, your fingers are pointing left, curl inwards, that means force is downwards. That's where the thumb is pointing. So yeah, this loop kind of expands a little bit, and it also resists you pulling it. So this force that is on this side is resisting your pull. And so it's opposing your motion. You need to apply a force as well if you want to keep it moving at a constant velocity. And so you also, let's say this is F1, you pull with F1. And so that's going to matter a little bit later. But let's calculate what this induced EMF is going to be. We got forces. Let's talk about induced EMF. So for that, we need Faraday's law, which requires magnetic flux. That's equal to BA cosine theta. This is not oriented anyway. It's just perfectly flat. Which means we don't need a cosine theta. Theta is 90 because it's perpendicular to the magnetic field. Well, yeah, okay. The surface of the loop is perpendicular to the magnetic field, but remember the area vector is perpendicular to the surface of the loop. So the area vector is actually parallel to the magnetic field. Theta should be 0 since we're using cosine. My bad. Cosine of 0 is 1, so that all works out. This is just equal to B times A. Now, what is B? Well, that's a given constant. We don't have to worry about it. What is A? A is the area of the loop that experiences a magnetic field. Last part is important. That's equal to length, this, times width, and the width is x of t, which we're just going to write as x. And so it's just going to be BLX. X, we need to know, changes with respect to time, though. Now, remember what I was going on earlier about this being with respect to time? That doesn't really play a role here because the magnetic field isn't changing with respect to time. The area is. But still, that's still important to keep in mind. Okay, BLX is the magnetic flux. So what is the magnitude of the induced EMF? Well, we just use that. Since we need magnitude, we don't really care about this negative sign. And so we just take the derivative of this with respect to time. So EMF is equal to derivative of BLX with respect to time. Well, B doesn't change with respect to time. We just establish it's constant. L also doesn't. You're not changing the size of the loop. X does, though. So the EMF is equal to BL. We can take this out. dx dt. Well, what is dx dt but velocity? Again, unit 1 of mechanics coming into play in unit 5 of E&M. That is actually pretty crazy. But yeah, pretty simple there. dx dt is v. And so the magnitude of the induced EMF is BLV. This is a very common FRQ problem for electromagnetism specifically. Like, it can ask you to work through all of this and calculate the force that is applied, or the energy you have to use, or the magnitude of the current, or whatever. You should probably know how to do this. Not just watch me go through it, but try to do one of these problems on your own with actual numbers. Or if they just give you like these variables, just use variables. It's going to be similar to this then. Okay. BLV, we know V, it's also one of our givens because that's just the speed you're moving it at. And even though there's a force on the other side, you're making sure it's constant velocity. Okay. Let's say, let's get another constant in here. The loop has an internal resistance R due to, I don't know, wires just having their own resistance, or maybe there's an actual resistor located somewhere on that. It doesn't matter. R is going to be our internal resistance. What would be the magnitude of the current then? I is going to be equal to EMF over R, because it's just Ohm's law, V over R. In this case, V is EMF, so it's just going to be BLV over R. Nothing simple, nothing complicated, nothing we can simplify there. Moving on to some other stuff we can find. What is this magnitude of the force? You probably thought we couldn't calculate that, but I'm actually going to ask you to calculate that. Again, like, pause for a second. This is a great review of some content, so just pause, see if you have any idea how to get that force. Just get an expression for it. Okay, I'm assuming you paused, but if you didn't, here's what you do. So remember last unit when we not only were able to find the direction of the force, we actually can calculate the magnitude of it using a formula. It's that the magnetic force on a current carrying wire is, the notation varies, but it's just equal to the integral of I dl cross B. This cross product is why there's a right-hand rule. Cross products and right-hand rules go hand in hand. No pun intended. And this is one of the cross products that we learned last unit, along with quite a few other. But this is the one we want right now. In this case, since they are not like, they're not vectors, they're just magnitudes. They're perpendicular to each other. Like, we don't need the cross product here. It's just going to be equal to ILB times sine of theta, because it's cross product. Theta, again, is going to be, well, in this case, theta is different. It's not the same theta as up here. Theta is going to be the angle between the current carrying wire and the magnetic field, which is 90 degrees. Sine of 90 is 1. So we don't need a sine theta. So the force is equal to ILB. We know L and B are constants that are given to us. I is equal to BLV over R. So you just multiply this by BL, and you're going to get force, F1 we called it, is equal to B squared L squared V over R. So that's the force. Oops. Okay. This force is constant because it's just made up of constants that don't change over time. So even though it seems like, hey, I'm pulling it farther, shouldn't the force on it change? Actually, no. Everything that would change gets canceled out, and the x over t becomes v, because and v is constant. We just established that a few minutes ago. Last thing, or one of the last things, is power. Power is force times velocity, or at least instantaneous power is force times velocity. So just multiply this by velocity. You're going to get power is equal to B squared L squared V squared over R, which looks fun. But you can also write that as BLV squared over R. Well, what is BLV but the EMF? So the power is just EMF squared over R, which is strikingly similar to the power like the power formula for a normal circuit, where it's equal to I squared R or V squared over R or IV. V squared over R is one of those forms. That's just EMF squared over R, which is great to hear. Or like connecting something in this unit back with something in like the first few units. Well, actually unit 3 because circuits. But anyway, point stands. It's actually pretty cool when you think about it. That's why I love this unit. Electromagnetism connects with electricity and magnetism. Okay. That is pretty much it for the first part of this unit. We just started this unit, and I know the content review has gone on for a pretty long time now. This is going to be a very long video. So that is all about Faraday's law and Lenz's law and induction. Now we get to move on to some of the more complicated parts of this unit. Yay. This one's electric fields. So what happens if you don't have a conductor, a closed conductor? when there's a change in magnetic flux. So let's say there's a change in magnetic flux this way, or there's a magnetic field, it starts to increase, decrease, what have you. There is no closed loop there to experience a magnetic, like an induced EMF. No matter, there's still going to be an induced electric field. In fact, that's the first step. A change in magnetic flux induces an electric field. That's what induces an EMF, and the induced EMF causes an induced current. We usually care about the induced EMF, or sometimes even only the induced current when we're looking at the direction only. That's just skipping a few steps ahead. The base part is change in magnetic flux causes an induced electric field. So what's the formula for that? Well, it's just an extension of Faraday's law. The EMF is equal to negative d magnetic flux with respect to time, which is equal to the integral with this weird little thing that's multivariable calculus, which you don't really need to know how to use, but or like you don't need the specifics of it, but you just need to know how to use it. So that's going to basically be like a surface or line integral, kind of, which we've used before when we've dived into E&M in previous units. So you should not be a stranger to this. So it's equal to E dot ds, where S is like the circumference of the loop. Well, I mean the imaginary loop. There's no actual loop there. So an example is if there's a magnetic field inwards and there's no loop there, then you're just going to induce a electric field that's not like a normal electric field, like going straight up, straight down, whatever. It's going to go in loops, in circular loops. So it's kind of like that. Because of this unique property of induced electric fields. And so that you just need to know it's not like a normal electric field. It's going to be concentric loops, which is pretty cool. One thing though, earlier when we were talking about electric fields back in electricity, we said electric field also causes electric potential. In this case, induced electric fields do not have electric potential, or there's no corresponding electric potential, because that's only caused by electric fields that are produced by static charges. This is produced by a changing magnetic flux. And so there's no potential difference, because this is what's called a non-conservative field. Okay. Short little subtopic there. Back to inductors, or inductance, and inductors, and induction, and circuits. We're going to get back to circuits. Again, I love electromagnetism for that. Okay, what is an inductor? So an inductor is a device that is used to produce a known magnetic field in a specific region. It's usually a solenoid. Like basically always it's a solenoid. And like a solenoid, or like a capacitor, because it's a solenoid, its value, or its strength of its magnetic field is determined solely by its physical characteristics. And what are those physical characteristics? So we have this, the formula, so this is solenoid, and the formula is that the inductance, which is a measure, kind of like capacitance for capacitors, the inductance for inductors is L equals, and L for inductance, not for length or whatever, it's equal to N, the number of coils total, times the magnetic flux over I. And you might be wondering, well, what about that magnetic flux? Well, it's just like how a capacitance is equal to, well, like the value of the capacitance is just based on its properties, but it's also equal to Q over V, right? And so these two aren't based on physical properties, but capacitance is. So given its physical properties, you can determine what the charge held on it is, or the potential difference across it is. So you would usually know what the inductance of a inductor is. So using that, the number of coils, and the current, you're going to get that, the magnetic flux. Okay. How else can we represent this? Well, we know that magnetic flux is equal to the integral of B dA, which, assuming there is no change in, or like, we can just write this as BA, and we're always assuming the orientation is like perfectly perpendicular to the magnetic field, so it's just BA, there's no theta. Well, when you add an N to that, which doesn't change much except for the fact that it just becomes NBA, basketball, whatever. So another thing you can do is replace N with NL, where N is the number of turns per unit length and L is the length. What that basically tells you is, hey, I have a solenoid that's like 50 centimeters, which is, wait, no, that's a really big solenoid, like 5 centimeters, and I have a solenoid that's 10 centimeters, but they both have the same number of loops per unit length. They're going to have similar properties, and so it's just useful to know. And we also know that the magnetic field of a solenoid is equal to mu naught times N times I. N lowercase n, because that is the number of windings or loops per unit length. So how can we combine stuff? Well, NL becomes N, mu naught Ni becomes B, and A just stays A. So it's NL times mu naught Ni times A. Well, N's combined, mu naught goes in front. Mu naught N squared La is going to be the inductance of an inductor. And as promised, all of this is just properties of the inductor. Mu naught is a constant, that doesn't matter. N is the number of windings per length, properties of the solenoid. Length, also a property of the solenoid. Area, which is like the area inside the solenoid, also a property of the solenoid. Like I promised, the inductance solely depends on the properties of the inductor. Physical characteristics. Unit of inductance is Henry. All of these are named after like famous scientists. For example, we have farads for capacitance. We've got coulombs. We've got volts. We got amperes. I don't know if I mentioned this, but the unit of magnetic flux is Weber, Weber. This is Henry, H. We got Tesla's for magnetic field. We got Gauss's technically for electric field. Also for magnetic field. It's just not used as common as Tesla's. Okay, anyway. I should probably stop rambling. So the inductance is this. You can also find the inductance per unit length, which is just dividing by length. It's just taking one thing out of the equation. Again, like I said, you might want to divide by length for a number of reasons, like showing that two solenoids that have the same number of loops per length but different lengths have similar properties. Okay, so now we can go back to two loops next to each other. In this case, they're going to be inductors next to each other. If there's a current in one coil, it causes a magnetic flux through the second coil, which changes, since that's a change in flux, because there used to not be a flux, now there is a flux. Since there's a change, there's going to be an induced EMF in the second coil. But there's also something interesting. There's also going to be an induced EMF in the first coil that is responding to that. Why? Again, maybe pause for a second, try to figure out why. This is called self-induction. Just think, what could cause this? It's a pretty interesting phenomenon. All right. So self-induction is pretty cool. Basically, it says that even though it has its own magnetic flux, it produces a magnetic flux, it also obeys Faraday's law. We know from this, if you just multiply both sides by I, we know that N times the magnetic flux is equal to Li. And if you consider that the EMF is affecting itself. So I told you to think about it, and what you would get if you think about it is that it causes, one way you can think about it is that it causes a change in current of the second loop because of the change in magnetic flux. That causes an induced current, which causes its own induced magnetic field. We already talked about induced magnetic fields, and that is a change in magnetic flux of the second coil, which causes a change in current of this first coil back again. So that's one way to think about it. Another way is just that it has a magnetic field. It produces its own magnetic field, and there's a current in that magnetic field, so it also gets induced by its own magnetic field. Because it's still in that magnetic field, there's a change in magnetic flux and so on. This the first way I described is more of mutual induction. This is more self-induction. But whichever way helps you remember that this occurs, you should use that. Anyway, back to this. So now to actually calculate the magnitude of the induced EMF, induced EMF, this L is to represent self-induction, is equal to negative d change in magnetic flux, but it's N times the magnetic flux, because this is a solenoid, so you basically multiply N times everything, pretty much. Well, we know that's equal to Li, and L doesn't change with respect to time. It's a constant for the inductor. So this is equal to, you can just take out the L, and you're left with di dt. Change in current over time. You probably didn't see that coming, because we've been talking about current is changing charge over time. Well, now it's the second derivative of charge. It's change in current over change in time, which doesn't have its own like value, unfortunately, like acceleration does. But you know, it's pretty important in this unit. So, okay, let's go through an example of self-induction. Okay, so you have a current going through an inductor. And let's say you have a resistor that's variable. So a variable resistor we haven't really talked about much, but a variable resistor can change its resistance. So it's denoted with this little arrow pointing to the resistor, just showing that like you can change the value of the resistance. So there's an EMF from the battery going down this way, because that's the positive end. So it goes through and around. If you decrease the resistance, though, that's going to increase the current, because V equals IR, or EMF equals IR. EMF is constant, so when you decrease resistance, you increase the current. And so that means that the current through this is going to increase. If there's an increase in current, what's going to change? It's similar to, hey, you want to oppose the change in magnetic flux. In this, you can just say, well, we don't have to go through all that like middle steps of finding the magnetic flux and stuff. Instead, you can just say, well, if there's a current increase this way, you're just going to oppose the current, because if you use the right-hand rule, you would find out that opposing the magnetic flux, the change in magnetic flux, is just the same as opposing the change in current. And so since current is increasing this way, you're going to want to oppose it by going up. And so the induced, self-induced EMF is going to be up. And yeah, that's pretty much self-induction. This is the formula, you should know that. And let's continue our discussion of inductors, but I need to clear the screen, because this one's a pretty long topic of inductors. We're going to be talking about inductors in circuits with other stuff in them. In this case, it's also going to have a resistor, which we kind of touched on in the previous example. We didn't really go through any numbers or formulas with it or anything, just like direction stuff. But if you have a current, if you have a circuit that has a resistor and an inductor, what is it going to be called? Well, let's see. Resistors are, and if you had a resistor and a capacitor, it would be RC circuit. Inductors L, what do you think it's going to be called? It's not RL, it's LR. But yeah, it's pretty self-explanatory there. It has an inductor and it has a resistor, so it's going to be RL. LR. We're also going to be talking about LC circuits, inductor and capacitor, but that's a little bit later. Let's get through this first. Now, what's common about this, or what's usually common, is that it's not connected. Instead, there's a switch. And it's currently at the A position. It could be at the B position. You can just switch it to the B position. So if it's at the A position, what's happening? So the current goes around like this, just in the outside loop. Basically what's happening is that the RL circuit, the resistor and the inductor are connected to the battery. So what can we do? We can use Kirchhoff's laws to write a differential equation for the EMF. And I'm not going to go through all the math because that's going to take way too long, and this is already a super long content review itself, and then we have 7 practice problems. So this is going to be easily more than an hour, more than maybe even 1.5 hours for this unit. So buckle in. Anyway, the EMF is equal to IR plus L di dt. I'm not going to go into why it's that, but use Kirchhoff's laws. An inductor in Kirchhoff's laws is similar to that to like capacitors and resistors. is just, we know the formula is negative L di dt, and you just take the negative of that, so it becomes plus L di dt. And IR is from Ohm's law for the resistor. Okay, so you can use this. This is a differential equation you can solve for I. You're going to get I of t, because it's time dependent, is equal to EMF over R times 1 minus e to the power of negative t over tau L. So it looks very similar to the RC circuit stuff. In this case, though, there's a tau L, which is the inductive time constant, and it's equal to L over R. I believe the capacitive, I don't know exactly what it's called, but for an RC circuit, is equal to 1 over RC. So this one's a bit different. And just, I'm going to point out something. L corresponds to 1 over C. They both refer to similar things. That's going to come up a bit later, and you might know where, because we're going to be talking about LC circuits, which have both L and C. But L takes the place of 1 over C. If you replace 1 over C with L in the second equation, you're going to get L over R. Just throwing that out there for a second. Keep that in mind. Okay. This is the formula for current in this specific scenario. Again, you're going to have to solve the differential equation or derive this using Kirchhoff's laws and then solve it. Maybe on the test, they might give you something, or they won't force you to derive it. You can just memorize it, but either way. What's interesting about inductors is inductors start by acting like a broken wire, and then eventually they act like a conducting wire. So at the start, there's going to be no current going through it because it acts like a broken wire, like a break in the circuit. And then it starts acting like a conducting wire. So the current approaches EMF over R, which is just the standard value for just a resistor in a circuit. But it takes some time to get there because inductors become conducting wires from being broken wires. And so if you were to graph the voltage through the resistor over time, it would be like an increase like this, because it starts at 0 because all the voltage is at the inductor, and then it starts to increase to this EMF over R level. That's the current. It increases to EMF itself. This is for the resistor. This is for the inductor. The current of that, or the EMF of that, would decrease from the level EMF to 0. And you can actually derive the equation for the EMF, because that's just equal to negative L di dt. You know I as a function of time, so just take the derivative and multiply by negative L. You're going to get a function for the EMF of the through the inductor specifically. If you change it to the B position, see, we only did half the problem here, which is very fun. Then your new equation would be IR is equal to negative L di dt. Don't ask me why. Well, okay, actually I can answer why. It's not that complicated. It's just, well, if you rearrange this, you would get IR plus L di dt is equal to 0. That's just equal to this, except the EMF is 0. And that's because you disconnected from the battery. It's just a closed loop like this. So there is no external EMF, which is why it's equal to 0. So yeah, that's the equation for point B. And again, you can do solving differential equations for that. It's going to be a bit easier because you don't have that equals EMF thing. But you're going to get I of t is equal to the initial current, which is EMF over R, times e to the power of negative t over tau L. Okay, it looks pretty similar, first of all, to RC circuits, where there's a change in the current equation depending on the situation, and one looks like this, one looks like that. Okay. Again, you can draw graphs for this, but they're pretty self-explanatory. The only weird thing is that the voltage across the inductor is going to be negative, and so it's going to look something like that, where this is 0 and this is a negative value. Is equal to negative IR. So yeah, that's pretty interesting. Okay. Our last topic for this is LC circuits. LC circuits are circuits that have both inductor and a capacitor. I'm not going to draw, there is no like battery in these because they basically charge themselves. And what I mean by that is it oscillates between charging itself. At one time, the inductor will be fully charged, and then at another time, it'll be completely empty and the capacitor will be fully charged. So it's just a cycle. And I'm going to go through that cycle right now. First of all, A little refresher, the formula for the potential energy stored in a capacitor is Q squared over 2C. Formula for potential energy stored in an inductor, that also has a formula. Let's see if you can try to guess what it is. I mean, if this is just a content review for you, you probably know what it is. But keeping in mind what I told you earlier, it's equal to Li squared over 2. And why does that make sense? Well, when it comes to inductors, current is the new charge. We've been talking about di dt forever. When it came to inductors, we were talking about dq dt, which is equal to current. Here it's all about the change in current, and so current is the base electrical value. Instead of charge, it's electrical current. Okay, why is the L in the numerator instead of the denominator? Well, that's what I said before. L takes the place of 1 over C. I'm not saying L is equal to it, but L and 1 over C appear in similar situations. And so since C is the denominator, you just take the reciprocal, so L is going to be the numerator in this case. So yeah, that was probably too much explanation of why that's the case, but if it helps you remember. I mean, it's on the equation sheet, I don't know. Okay, so let's go through this oscillation. So the capacitor starts with maximum charge. So there's this electric field going through it. There's plus, minus. And what happens is that all the potential energy in the system is in the capacitor, none in the inductor. So there's no current at all because everything's charged. There's no current because there's no potential energy in the inductor. Then the capacitor starts to discharge. This is the second step. If the capacitor starts to discharge, that means the current starts to flow this way, which means that there's going to be a magnetic field caused by the inductor. And so now there's going to be roughly even amounts of capacitor potential energy and inductor potential energy. Then you fully discharge the capacitor, so there's no electric field going through it. This is now 0. This is now its maximum. It's like a pretty big magnetic field around it. And then the capacitor starts to charge, but in the opposite direction. This becomes positive. This becomes negative. And so it goes in the opposite direction, and the current starts to decrease. And then it gets fully charged. There's no current again. This is now completely full. This is now 0. And then it starts to go in the opposite direction. This time current goes that way because the capacitor discharges. It's now in the opposite direction. It's discharging in the opposite direction. There's another magnetic field, but it's in the opposite direction. So now they're about half and half. And then capacitor fully discharges again. Current again. There's a lot of magnetic field again. This is full again. This is 0 again. And then final phase is that the capacitor starts to charge in its original direction again. Sorry if I'm saying again too much, but it's basically a repeat. It's periodic. And so it starts to charge in the original direction again. That doesn't mean that it's fully charged, but the next step is that it is fully charged, which is the first step of the entire cycle. So it just keeps going on back and forth. I didn't draw it to my full extent because we're running out of time, but that's pretty much how it is. You can look up a video or a photo of it online to show the entire cycle in one. Okay, why is this interesting? Well, it's basically an oscillation, and so you can relate it to like simple harmonic motion, specifically springs, where the charge is basically equal to the position of the spring, and the current then is the velocity because it's the rate of change of the charge. And the two constants are 1 over c is k, the spring constant, and L is m. Why is that the case? Well, if you look at springs, 1/2 kx squared is plus 1/2 mv squared equals 0. That means that this total sum of the, or not equals 0, equals the total energy, right? Potential energy in the system. That says that the energy is constant and it just oscillates between those two forms of energy. Well, in this case, if you write it a different way, it's 1/2 1 over c times q squared plus 1/2 L times I squared, which is the same thing if you consider this to be that, k to be 1 over c, v to be I, and m to be L. And that's equal to the total energy. So what's interesting is that the frequency of this oscillation is an angular frequency of 1 over square root of LC. pretty cool. You should probably know that, or at least know how to derive it. Specifically know how to derive it, because there can be some problems that arise from that. And like I said, the total energy present in the system is given by this formula, which I kind of drew over a little bit, but hopefully you still understand what that means. And since we assume circuit resistance to be 0, no energy is transferred, and so U, or in this case E, total energy, is constant over time. How does that help us? Well, that means du dt is 0, which means that the rate of change of this one, well, if I use these formulas, it becomes q squared over 2c plus li squared over 2. Rate of change of that is equal to 0. And if you do a bunch of math there, which I'm not going to do because we're definitely running out of time, you're going to get a differential equation in terms of charge, which if you solve, you're going to get q of t. The formula for it is the initial charge times cosine of omega t plus phi, where omega is this, and phi is the phase angle. It just changes the starting of the oscillation. And so yeah, that just proves that it's an oscillation, just like simple harmonic motion. You can also get similar formulas for current, which is just the derivative of this, because current is derivative of charge with respect to time. Then once you find current, you can find EMF L, the self-induced EMF, because that's just equal to negative L times di dt. So you take the derivative of current and multiply it by negative L. And if you solve all of that, actually, you're going to get U is equal to q naught squared over 2c, which seems pretty obvious because we started with the capacitor fully charged. But somehow we did a lot of math and found that out. I didn't show all that math, but you can actually do every single step, do a lot of simplification through algebra, and you're going to get that as the end, which, in my opinion, you could have figured that out from the start, but, you know, fun. Math is fun. All right. Finally, that is the end of our content review. That is pretty much 1 hour of just content review. So it's time for the practice problems, which I'm actually going to speed through a little bit because it's been so long. I did not expect it to be this long. But hopefully you understand the main gist of it. We got 7 problems today. Most of them are pretty calculator heavy, which is why I'm going to speed through it a little bit. Some of them are pretty conceptual though. All right, starting with this first one. It's a coil, 4 centimeters in radius, 500 turns. This is just the formula for, this is just Faraday's law, because it's asking for the induced EMF as a function of time. It gives us magnetic field as a function of time. And so the induced EMF is equal to negative, technically, but since it's just the magnitude of it, this. Change in flux over time. But it's a solenoid, so we need that N in front. Because every time you deal with magnetic field or flux in a solenoid, you have to have that N, because it's just how it goes. It's just looped N times. Okay. Well, this magnetic flux is equal to B times A, because it's perpendicular to the field. There's no theta. And so you can also take the A out, because the A is not changing. So it becomes NA times dB dt. Na, both don't change, B does change by this equation, so you just take the derivative of the equation B equals 0.012 t plus 3 times 10 to the power of negative 5 t to the power 4, and if you do, you're going to get dB dt equals, well, you're going to have to multiply by N and A, so N is 500, A is the area, which is, pi r squared, pi times 0.04 squared, because 4 centimeters. So if you multiply all that out and take the derivative of this, so taking the derivative and multiplying all that, you're going to get 0.0302 plus 3.02 times 10 to the power of negative 4 t cubed. That's equal to the EMF. So that's the formula for the induced EMF. The current, well, first things first is current is equal to EMF over R, so it's just equal to this entire function divided by 600 ohms. And you just plug in T equals 5. So if you plug in 5 into that, you're just going to get a current, an induced EMF of 0.0680 volts, because just plugging 5 in there. And then divide by 600 ohms, you're going to get a current of 1.13 times 10 to the power of negative 4 amps. And so that's going to be your induced current at 5 seconds specifically. Okay, that was just simple Faraday's law. This next one focuses on Lenz's law. Is just purely conceptual. So we got this loop. In this outer loop, there's going to be a sudden change in current, which is going to cause a magnetic field, which is going to induce a current in the smaller loop. So we need to figure out the directions. So A, just after switch C is closed, switch S is closed. So as soon as it's closed, in that instant there's a current, change from zero current to some amount of current. And so that's going to induce a EMF in the smaller loop. What direction is that current? So this is the positive end, this is the negative end. So current is going to be going this way. So what direction is the magnetic field? Well, you turn your fingers counterclockwise, which means your thumb points outwards. So unfortunately, that means we're just going to have to draw dots instead of X's, but it is what it is. We've got dots coming out of the page because magnetic field is out. It starts at 0, then becomes out. So the change in magnetic flux is outwards. And so the induced magnetic field would be inwards. Induced magnetic field is inwards. Again, you use right hand rule. You point your thumb inwards. So what direction is the fingers curling in? They would be curling in clockwise. And so the direction of the induced EMF or induced current is going to be clockwise. Okay, that was just part A. Part B, after it's been closed a long time, well, if you think about it, there's no change in current after it's been closed a long time because it's just the same current going over and over again, so there's no change in magnetic flux. There's still a magnetic field being produced, but there's no change in magnetic flux, so there's no induced EMF or induced current. So part B is there's no induced current. Part C, you reopen the switch after it's being closed for a long time. So now there's the opposite change. So there used to be a current this way, meaning a magnetic field outwards. And then the magnetic field becomes 0 because there's no current anymore because you open the switch. So it goes from outwards to 0. So the change in magnetic flux is inwards. Outwards to 0 is a net change inwards. And so your induced magnetic field would be outwards. And so again, using right hand rule, thumb points outwards, and so your fingers have to curl wrong way. Fingers have to curl this way, which is counterclockwise, and so the current in the smaller loop is going to be going counterclockwise. Okay, 2 problems done. Third one, this is what I was talking about, this entire problem about motional EMF. We went through basically the entire thing in the content review, but this time it gives us value, so we're going to have to resolve everything. Okay. Find the magnitude of the EMF induced in the rod when it's moving towards. Again, I told you, this is the one where the rod changes, so the area does change. It's not like the area specifically of the magnetic field is the entire area of the loop. Also, I went through the entire derivation process in the content review. That's probably why it took so long. I'm not going to rederive it here. I'm just going to say, this is the formula we derived in the content review. You should know how to derive it. I'm just going to plug stuff in here. So on the actual FRQ, you're probably going to get an FRQ that looks like this. This entire thing with this has D, you're probably going to get to like F or something. And that each step is going to be like you derive a little bit, plug in values, or if they don't give you values, just derive a little bit, get an equation, derive a little bit, get an equation. I'm just skipping the derivation process because I derived basically everything you would have to derive in the content review itself. And anything else is not part of this unit. It's just like a review. For example, the power, if I didn't do that, that would just be review. So you should have known how to do that. I just did it because it's a pretty common question they would ask. Okay, rant over. What's the magnitude of the EMF? Well, as we know, the formula for the EMF is BLV. And so the magnetic field is 0.8 Teslas. Length is 50 centimeters or 0.5 meters, and velocity is 7.5 meters per second. Multiplying them just gives you 3 volts. It's as simple as that. In what direction does the current flow in the rod? Okay, this is Lenz's law. If you're moving the rod this way, you're increasing the area. Magnetic field is going inwards. It goes even more inwards, or change in magnetic flux is still inwards because your area is increasing, so the magnitude of the magnetic flux is increasing. So the net change in magnetic flux is inwards, so your induced magnetic field is outwards. If your magnetic field is outwards, we just did this, you would have to go counterclockwise. So the direction of the the direction of the current is counterclockwise. Or you can say it's from B to A. It said specifically in the rod, right? So if it goes counterclockwise, it has to go from B to A, is probably what you would write. Counterclockwise would probably not get you the point since it's specifically about the rod, not the loop. And you can't really go counterclockwise in the rod itself. So you would go upwards or B to A is what you would say. Okay. C, you want to calculate the resistance of the entire circuit if, the current of the entire circuit if the resistance is 1.5 ohms. So you just do 3 over 1.5 is equal to 2 amps. Just as simple as that, basically. Sorry, no, you don't calculate the current. It's find the force. So yeah, okay, there's more to this problem than what I originally thought. Find the force required to keep the rod moving to the right with a constant speed. So that's basically saying, what is the force on the rod in the opposite direction? The opposing force generated by the current carrying, the fact that there's a current carrying wire in the magnetic field, it's equal to the force that you have to apply because you're keeping it at a constant speed. So, force is equilibrium. You remember that. And so just what is this force? Well, we know FB is equal to integral of I, or lowercase I if you want, dl cross B, or just ILB, because there's no angle here. Well, it's perfectly perpendicular, so sine theta, sine of 90 is 1 again. And there's no weird stuff where you have to actually integrate, so you can just multiply them. Current is 2 amps, length is, again, 0.5 meters, because it's just the rod. And then B is 0.8 Teslas. So you just do 2 times 0.5 times 0.8, which gives you 0.8. So force B is 0.8 newtons. And so F1 is 0.8 newtons to the right. Because it is asking magnitude and direction. So it's to the right, positive, whatever works. That's pretty much it for C. And then for D is compare the rate at which mechanical work is done by the force. FV. So this is power. Like I said, pretty common question they can ask you. You just do 0.8 times the velocity, which is 7.5, which is equal to, since they didn't say power, I'm just going to write FV is equal to 0.8 times 7.5, or 6 watts. And then they're also asking the rate at which thermal energy is developed, and they actually give you the equation. They might not, and you might have to remember back from the circuits unit that it's equal to I squared R, or IV, or V squared over R. In this case, I squared over R works because we got 2 amps, so it's 2 squared, times resistance of 1.5 ohms, so it's just 4 times 1.5, or 6 watts. So it's so all the work that's being put in to move it is being released as energy, and we know that because there is no net force on the rod. It's moving at a constant speed, and so you're not really changing the force, so you're not putting any energy into that. All the energy is leaving the system as thermal energy. So conservation of energy. That's your short answer. Okay, that was one of the longer questions here. So we're only done with 3 questions so far, but we still have these 4 more left. Okay. Long thin solenoid, 400 turns per meter. So this is 400, lowercase n because it's per unit length. Radius 1.1 centimeters. Current is increasing at didt. Find dt if the induced electric field. Okay, we're talking about electric field now. So the formula is EMF is equal to negative d change in magnetic flux over time, which is equal to the integral of E ds dot product. And so you can use that here. In this case, though, we know, since this is like a integral that occurs over the circumference of the circle, not over the area, this is just equal to E times the circumference, or 2 pi r. So it's just 2 pi re. And we know magnetic flux is B times A, and A doesn't change. And so you can take out the A. And the formula for the magnetic field of a solenoid is mu naught times N times I times, times I, and mu naught N I. And then you multiply it by the area, because That's magnetic flux. And none of those change with respect to time except I. di dt does change, it says so in the problem itself. And so this becomes negative mu naught Na times di dt is equal to 2 pi r e. And the negative sign does not matter because we're just dealing with magnitudes here. Okay, that means that isolating for di dt, it's equal to 2 pi r e over mu naught Na. And we just have to solve for di dt. So plug in what we know. R is 0.011 because 1.1 centimeters. E is 8 times 10 to the negative 6. N is 400. A is pi r squared. Actually, so the pi and pi cancel. And this r actually cancels with one of the r's here. So that actually is 0.011. So if you want to simplify it a little bit, you can. But it doesn't really matter that much. One thing, sorry. Actually, this is a little bit misleading. That R actually doesn't cancel because that's a different R. I'm going to call this capital R down here. That's 0.011. That's the radius of the entire thing. That's the area inside the solenoid. But this is actually 3.5 centimeters from the axis. So if you think of the solenoid like this, like this, that's the entire radius of it. And then this is just 3.5 centimeters from the axis. So looking at the cross section, that's the entire area. This is the circle that you're dealing with. And so the smaller r here is going to be this 0.035 centimeters. Or, which is actually bigger. Sorry, it's the outside. Because 3.5 centimeters is bigger than 1.1 centimeters. So ignore what I just said for the past second. But that you're going to plug in 0.035, not 0.011 into the numerator. Okay, anyway, plugging all this in, you're going to get di dt is equal to 9.21. And the unit for this is amps per second. There's no specific unit. Like I said, no actual value that describes the rate of change of current over time. Okay, that was that problem. Next one. When the current in a toroidal solenoid is changing at a rate of 0.026 amps per second, the magnitude of the induced EMF is 12.6 millivolts. When the current is 1.4 amps, the average flux, okay, blah, blah, blah. How many turns does the solenoid have? Similar problem. In this case, L is equal to N magnetic flux over I. That's one equation we know for inductance. And also we know L is equal to EMF over di dt. Why? Because EMF is equal to L times di dt. That's on the equation sheet. Technically negative L, but we're dealing with magnitudes here. Okay, so combining those two, we get N times the magnetic flux over I is equal to EMF over di dt. And you're going to want to solve for N. So multiplying both sides by I and dividing by magnetic flux, we get EMF times I over magnetic flux times di dt. And we just plug in what we know. EMF is 12.6 millivolts or 0.00126. Sorry, no. You can just write in scientific notations. 12.6 times 10 to the power of negative 3 volts. Current is 1.4 amps. di dt is 0.026 amps per second. And magnetic flux is 0.00285 Webers. And so plugging all that in, you get N is equal to 238. And so that's just going to be 238 turns. All right, that was relatively simple. Two more problems here. An RL circuit or an LR circuit and then an LC circuit. So for this LR circuit, you have... so this is the standard diagram where you got two switches here. In first switch, S1 is closed. And then S2 is open. So it's only this part of the circuit that's in play. So we got this battery here. Positive side's this side. We got switch closed. Switch closed. On this side, we got resistor and inductor. Okay, that's pretty much all the circuit that really matters right now. Inductance is 0.115 henries. resistance is 120 ohms. And energy stored in the inductor is 0.260 joules. Okay, so we know that in an inductor it's equal to 1/2 Li squared, or just Li squared over 2 is how I showed it in the content review. Both work, they're the same thing. And we can find the current by just multiplying both sides by 2, dividing by L, and then square rooting. And we know all of this. The current is, or the energy is 0.296, sorry, 260. I don't know where I got the 9 from. 260 joules. And L, the inductance, is 0.115 henries. I don't know why I think there's another 0 there, but there isn't. Okay, you plug in the values, you got I equals 2.13 amps, not 213. 2.13 amps. Okay, and it's asking for the EMF, so that's just equal to the current times the resistance, Ohm's law again. So that's 2.13 times resistance is 120 ohms. And so you just multiply them out, you get EMF is 256 volts is your answer. For part B, after the current reached its final value, S1 is opened, S2 is closed. So that's open, that's closed. And so now what's left in the circuit is resistor, inductor, that's it. No battery, or no EMF, external EMF. Okay, how much time does it take for the energy stored in the inductor to decrease to 0.13? Okay, so we know that the formula for this is current is equal to initial current, or EMF over R, but we know EMF over R is already 2.13, so we can just write initial current times e to the power of negative t over tau L, which tau L is L over R, and so you can also rewrite this as negative R over L times T. Because just 1 over tau L is R over L. Okay, and plugging in what we know, first we need to solve for the formula, the equation that describes the energy over time. That's just equal to 1/2 Li squared. So you just do 1/2 L times I naught squared times e to the power of negative 2R over LT. Which, yeah, that's pretty much it. And you wanted to find out when this is equal to 1/2 the original. And the original is 1/2 Li squared, so this becomes 1/4 Li squared. And the I naught technically, and the I naughts cancel, the L's cancel, and you multiply both sides by 2, and you're gonna get 1/2 on this side, and you're gonna get rid of the 1/2 there. So just 1/2 equals e to the power of negative 2R over L times T. And so if you ln both sides and then multiply by L divided by 2R, you're gonna get T is equal to negative L over 2R ln 1/2. ln 1/2 you can calculate. We also know L is equal to 0.115. I got it right this time. R is equal to 120. Plugging in values, you're going to get a time of 3.32 times 10 to the negative 4 seconds, which is very small, but everything we're dealing with in this unit is very small. It's just minute differences in current, which causes an induced magnetic field and an induced current and so on, just in very small spaces. And yeah, that was that problem. It was just 2 parts. The second part was the time, which we calculated. Okay. Last problem here. This is an LC circuit. 18 microfarad capacitor is placed across 22.5 volt battery for several seconds and then is connected to a 12.0 millihenry inductor. Okay. Inductor, capacitor, that's it. Okay. We know that this capacitor is completely charged, fully charged, because it was just connected to a battery and then removed. That's the entire reason it was connected to a battery. That's, if they didn't mention that at the start, then nothing would happen, because the capacitor is not charged, the inductor is not charged, So it's just going to be a boring circuit. But they told us that they charged the capacitor. So after the capacitor and inductor are connected together, find the maximum current in the circuit. So currently the current is 0. No pun intended. Because the capacitor is completely charged. But we can set the initial capacitor energy to be equal to the magnetic flux, the inductor energy, because when this is completely full, this is 0. When this is 0, this is completely full. And we want when the inductor is completely full or completely charged, because that's when the current would be the maximum. And so this becomes Q naught squared over 2C is equal to Li squared over 2. The 2's cancel nicely. And we're solving for I. So we divide both sides by L and square root. So square root of Q naught squared over LC. And you can just plug in what we know. So this is 12.0 millihenries. So that's just 12.0 times 10 to the power of negative 3 henries. That's 18 microfarads. So 18.0 times 10 to the power of negative 6 farads. And Q naught, which you actually don't know. So that's a little bit tricky thing. So there's two things you can do. One, change the equation you're using for this, because there's multiple equations you can use for the energy stored in a capacitor. There's also 1/2 CV squared. But if you already started doing this, you can just say, well, Q is equal to CV, so Q naught is equal to CV. C is, well, there's two things you can do. You can plug that in the new equation, or you can solve for current, or for charge. I'm going to plug this into the equation because I like getting a final equation before plugging stuff in. So that becomes C squared V squared, because it's Q squared. One of the C's cancels with this in the denominator. And so I'm just going to write. So it becomes CV over L. Sorry, CV squared over L. And you can take the V outside, actually, because it's square root of a square. So I just changed the equation a lot, but it's V times the square root of C over L. And the C is now pointing towards this, not that. And V, we do know, is 22.5 volts. And so plugging everything in, we get current is equal to this times the square root of that, which is 0.871 amps. That is what they wanted. Yeah, maximum current. And when the current is maximum, what is the charge on the capacitor? Say it with me, it's 0, because when the when the inductor is completely charged, the capacitor is not charged at all. And so this is the maximum. That means this is 0, so charge has to be 0. And so, yeah, charge is 0 at that time. How long after the capacitor and inductor are connected together does it take for the capacitor to be completely discharged for the first time? Well, we know that there are equations for this. We know that omega is equal to 1 over root LC, which means that T is equal to 2 pi over omega. And so T is equal to 2 pi root LC, because 1 over root LC is just root LC. And so plugging it in, L is, again, 12.0 times 10 to the negative 3 henries. C is 18.0 times 10 to the negative 6 farads. So, calculating that, you're going to get T is equal to 2.92 milliseconds, or just 2.92 times 10 to the negative 3 seconds. And so how long does it take for the capacitor to be fully discharged? So what's the entire period? So the step is capacitor is fully charged, then they're pretty much equal. Then this is fully charged, then they're pretty much equal again. Then capacitor is fully charged the other way, and then they're equal again. Then this is fully charged the other way. Then they're equal again. And then capacitor is fully charged again. So that's quite a long period of time. So it's 1, 2, 3, 4, 5, 6, 7, 8. 8 steps is the period. And we want to get to the capacitor to be fully, completely discharged for the first time. That's this. That's when the inductor is fully charged, so the capacitor is fully discharged. That's 2 steps. So it's 2 out of 8, or t over 4. It takes t over 4 seconds to... It's 1/4 of the entire period. And so you just do 2.92 times 10 to the negative 3 divided by 4. You're going to get time is equal to 0.73 times 10 to the power of negative 3 seconds, which is not proper scientific notation, but it's fine. And then for the second time, well, that's going to be this step right here, because capacitor becomes fully charged in the middle and then back to fully discharged. So it's 1, 2, 3, 4, another 4 steps. So 6 steps. 6/8 is 3t over 4. So you just multiply this by 3, you're going to get 2.19 times 10 to the power of negative 3 seconds. So that's for the second time. And then finally, sketch graphs. We might be running out of space, but just very small. For charge and current. So charge starts off positive, then it becomes negative, and then positive, and then negative, and then positive, and so on. It's just an oscillation. The reason why charge can become negative is because it gets charged the opposite way. That's what the negative charge means. For current, it's gonna start off at 0, then it's gonna become positive when this is 0, and then 0 when this is negative, negative when this is 0, 0 when this is positive, positive when this is 0, and so on and so forth. So it's just going to be mirroring that, but opposite. And so they both are just sinusoids. One is like sine, one is cosine. So yeah. And that is the end of the problems. All of the problems are done. Content review is done. We are done with electricity and magnetism, or electromagnetism. We're done with this video. But more than that, we're done with all of AP Physics C, every single unit, from the start of mechanics, kinematics, all the way to electromagnetism. And yeah, this is the final video in that series. So good luck on this test. Good luck on the AP exam and any physics you do at any point in time. So good luck, and I will not see you next time because there are no more AP Physics C videos, but good luck anyway.